Okay, so good afternoon again. Let me share the screen. Okay, here we are. So just wanted to tell you that I included just now the calendar of the exams in the webpage of our course. The webpage is this one, lecture notes. If I go to the bottom, I get the calendar of the exams. 1 second, here it is. I think we already discussed these dates, so there is nothing new on my side. So if for some reason you see something that it's not correspondent to what I anticipated, just let me know, but I don't think so. And I already mentioned to you that for those who have the need of taking the exam earlier, and in particular for the Erasmus students, we will find the solution, okay? For the Erasmus students only, because for the other students, I cannot find any other solution. I cannot anticipate the exam date before June 17, but for the Erasmus students, we can find a solution, okay? And it's not the time now to discuss it. Just let me know later on in April, in May, you can contact me and say, look, I have the need to, I am leaving earlier than June 17, I need to take the exam earlier. And once again, we find the solution. I also mentioned to you that for Erasmus students only, please, can you please stop talking? Thank you very much. As you know, I cannot really speak if someone else is talking. I'm sorry for that. And I already mentioned to you that if also there is the option only for Erasmus students to eventually take the exam online, only for Erasmus students and only, I mean, after discussion, because for any exam that is taken online, I need to ask permission to the university, and they check your career, check if you indeed left earlier than the first exam date, etc. So just let me know, contact me if you have any need, and be aware that for taking the exam online, it's not easy. So I prefer to schedule an exam in physical presence earlier than these dates, only for Erasmus students. Hope it's clear. Do you have any question? Okay, good. Now, we were talking about climate models last time. So let's go back to the point. Just let me take the slides. We got somewhere here, just 1 second. Here, we got to this figure now. Just remembering to you what we are talking about. We are talking of models, and about models, we basically explained that these models, to make it very short and very easy, these models are based on conservation equations, can be conservation of mass, conservation of energy, conservation of heat, whatever. These conservation equations are expressed in differential form. We explained why. Okay, so the equations describe the changes of any variable we are interested in, like temperature. And these equations are applied to elementary volumes. And there are millions of elementary volumes to cover the atmosphere and the Earth, because our domain is not only the Earth, it's also the atmosphere. And then we get millions of equations to be solved simultaneously. And this is really complicated, needs supercomputers. Perfect. On the other hand, we explain why we need to divide in elementary volumes, because conservation equations describe changes in variables, the average change in variable inside the volume. So for each volume, we get a value of temperature, which is the average for that volume. And therefore, if we want to describe locally the temperature, we need to split the domain in volumes. And the smaller the volume, the better it is, because given that the equation describes the average within a volume, you understand that if the average is computed on a big volume, it is less informative than an average computed on a small volume. So we need to split in very small volumes. And this makes the number of equations to be solved simultaneously so large, millions. And this is why we need supercomputers. The individual equations are not so complicated. They are quite simple. If you think of a mass balance, for instance, you have a small volume. The mass balance is just that the total mass inside the volume of a given quantity is conserved. So if you have an inflow of mass and an outflow of mass, so let me just write in the blackboard because I think it is more interesting. And probably the best blackboard is this one. Let me make sure that the camera looks at the blackboard. Very good. So let me just check from here to here. Okay, good. Let me write on the blackboard then this concept because it is very simple. So what are we talking about? Conservation equation, okay? Conservation equation. I think it is interesting to dedicate some time because this is really the basic. And it is also a simple basis. So this is why I want to dedicate some time. Of course, you can find in Wikipedia a page, an item on conservation equations. So if you want to expand your knowledge, it is very easy. Okay. And for instance, let's talk about conservation of mass. Conservation of mass. Mass of what? Something. For instance, water. Okay, so we have this small volume. Now it is in 2D, but you have to think of this one as a volume. Let's make it in 3D, okay? So you have a small volume. Let's call it V. And I want to say that the mass of water inside the volume is conserved. Conservation may be something of misleading term because conservation, you may get an interpretation of conservation like unchanged. Actually, it is more articulated. So let's suppose that you have some mass of water getting into the volume in, and you may have some mass of water getting out, volume out. Okay. So conservation means that, and also you have inside the volume a storage. Okay, let me put it here. A storage of water. So some water that is inside the volume. So you have a volume of air, for instance, with some water into it. And then you have some water flowing in and some water flowing out. The conservation equation is very simple. It says that if I make a difference, input minus output, in minus out, then the difference should be equal to the change in storage. Let me write it, okay? And in differential terms, I need to write it in differential terms. It is something like delta W in divided by delta T. What is T? It's time. So I get, for instance, 1 hour. And I say, okay, or let me just show, sorry, the delta is not a good idea. I made a mistake. Okay, let me restart. W in minus W out. This is the difference that I mentioned before. Okay. This difference should be simply equivalent to the change in storage. Here it is when I get the change in storage divided by what? Time. So the volume in minus volume out are measured in a time step. This is when I get to introduce the time step. So if you say some water comes in, you have also to say in what time, in 1 hour, in 1 day, in 1 week, whatever, okay? But you have to define a time step. So volume in minus volume out in that time step, it's equivalent to the change of storage divided by the T. Yeah, okay. And here I have to divide by time. Okay. So indeed, volume in during the time step minus volume out during the time step is equal to the change of storage divided by time. And you see that this is dimensionally consistent, because here I have a volume divided by time, and here I have a volume storage is a volume divided by time. Okay. You see, it is very simple. I'm sorry that when introducing it, I made a little bit of, I need to make a little bit of corrections, but you see that it is very simple. So I have to refer to a time step, and volume in minus volume out is equivalent to the change of storage during that time step. And you understand from this relationship why it is a change. Because if the variable I'm interested in is the storage, this equation is describing the change of storage. Not really the storage, it is describing the change. So there is a very simple reason why these equations are in differential terms. On the other hand, you see that the differential terms, it is a very simple concept, it's a difference. It is not something complicated, so you don't have to be concerned if you hear about millions of differential equations. The only complicated thing is the number, millions, but the differential equation, it is very easy. It's very easy. Okay, so what we said is the complication is given by indeed it is indeed given by the number of equations. If I want to make the model simple, then I can just reduce the number of equations, reduce the number of the elementary volumes there. And for instance, I made an example of a very simple model, which is one model for describing temperature, but I want to describe the average temperature of what? Of the Earth's atmosphere. Okay, of the Earth's atmosphere, so the temperature in the air here. Okay, average over the whole Earth. Then the volume becomes just one. Okay, and we got to this simple model. This one. Okay, when I introduce the simple model, whose solution is consistent because this is based on relative equilibrium. And if I want to describe temperature, here is the average temperature over the whole atmosphere. If I want to describe it from this equation where I know everything, because S is the solar constant, the incoming solar radiation per unit area, A is the albedo, as I said, R is easy, is the radius of Earth, and sigma is the Stefan Boltzmann constant. Epsilon is effective emissivity. I said, I know all of these, they are here. And if I want to get an explicit representation for the temperature, what I said was, here it is, and I get a result of about 15, which is okay. I mean, if I want to get an average estimate of the full temperature of Earth, 15 degrees is reliable. It is what we know. Okay. Let's forget about global warming. There are no digits here, just 15. Okay. So it is fine. And what is the purpose of this simple example? The purpose is to show you that the equation actually is very simple. It is based on conservation of energy. It is very simple. Then some of you asked me a question, and the question was very pertinent. So some of you asked me, what is the albedo, what is the lucidity? Indeed, I introduced this model very quickly. So it is not, the comprehension of this model is not immediate. And therefore, I thought that indeed this is true. I thought that to make this example more educational, I need to give more details. And therefore, what I did is I modified the web page and I added one more figure, which I want to discuss with you today, because as I said, I think it is a good example. And this is the figure. This is a sketch which describes better this model. So what does it mean, the radiative equilibrium? That we have to equate the power, the energy that we get from the Earth, from the space, with what is emitted by the Earth and the atmosphere back into space, and what is trapped into the atmosphere. So if you consider the atmosphere as an elementary volume, a big one, in this elementary volume, you have something entering, W in, okay, something entering, something going out. So we have solar energy getting into the atmosphere. Part of it is emitted back into the space, and part is trapped. It's stored, it's the storage. And of course, if we study the equilibrium, we can describe temperature. Why? Because, okay, what we get from the sun is fixed. It doesn't depend on the temperature of the atmosphere. But what is emitted back depends on the temperature of the atmosphere. And what is stored depends again on the temperature. Because, of course, if the atmosphere gets warmer and warmer and warmer, then it means that it stores part of this energy. And therefore, at a certain point, we reach an equilibrium. An equilibrium between what we get from the sun, what is emitted back depending on temperature, and it increases. So on increasing temperature, I emit back more than that, and what is stored, which is related to temperature again. And of course, this sketch is also useful because it allows us to understand where is climate change. So what is the greenhouse effect? And you see here, greenhouse effect. It depends on what is emitted back and what is trapped, of course. The more we trap into the atmosphere, and the more the temperature of the atmosphere increases. And this is where we have climate change. So let's describe then what we get from the sun. And what we get from the sun is described by a value that we know. It's the power that we get from the sun per unit surface. Okay? And the unit surface of what? Of a sphere. A sphere. Okay? And then we get part of it, which is reflected back. And this is defined by the albedo. Okay, so let's look at what is the definition of albedo. And you can find it here. Albedo, there is a link, Wikipedia page. The albedo is the fraction of power in the total electromagnetic radiation, okay? Because from the sun we get a radiation. And the albedo is the fraction of power that we get from the sun that is scattered back into the space. So the albedo is the part that it is directly, once that the sun radiation reaches the atmosphere, it doesn't get into the atmosphere, it's just reflected back. Okay? And so you get here this yellow arrow. There is no, it is just reflected back. And the albedo is about 0.7, 0.68. Okay? And then we have a fraction, which is 1 minus the albedo that gets over the Earth. Why it is divided by 4? It is divided by 4 because we need to compute the surface projected on a plane which is projected over the circle of the Earth. So the surface is computed over the surface of a sphere, but part of this radiation is just hitting the sphere tangentially. We need to project the radiation over the circle. The section of the Earth is a circle. And this is why we divide by 4, okay? Because you may remember the volume of the sphere is 4 pi r squared, not the volume. The surface of the sphere is given by 4 pi r squared. R is the radius of the Earth, and the surface of the circle is pi r squared. So there is a factor of 4 of difference, and this is why here it is divided by 4. Okay. Now, when you get to the Earth, there is the Stefan-Boltzmann law, which we don't look at it in detail, okay? Just remember from, if you had some background of physics, the Stefan-Boltzmann law describes the power that is emitted by a body depending on its temperature. Okay? And the Stefan-Boltzmann law says that what is emitted back depends on temperature to the power of 4. Temperature of the Earth itself, and then multiplied by the Stefan-Boltzmann constant, okay? And the Stefan-Boltzmann constant, you know the value because it is given in my lecture notes, but let's forget about, but we don't have to get into the details of the Stefan-Boltzmann equation. Just let's take for granted that if Ts is the temperature of Earth, the power that is reflected back is given by sigma, which is, once again, Stefan-Boltzmann constant, multiplied by the temperature of Earth at the power of 4. Now, there is some difference between the temperature of the Earth and the temperature of the atmosphere. It is small. We don't want to, okay, to focus on this difference now. But this is why here you see Ts for the temperature of Earth, which means Ts stands for surface, and here you see T for the temperature of the atmosphere. They are similar, but actually, if we want to be rigorous, the quantity that is reflected back by the Earth, the body of the Earth, depends on the temperature of Earth, not the atmosphere. They are close, but there is some difference. Also, let me say that the temperature of the atmosphere, to be very rigorous, we should make a difference between the lower atmosphere and the upper atmosphere. So let's just use T to say temperature of the atmosphere, and let's assume that it's constant, because this is a very simplified model describing the average temperature. Okay, but actually, if you want to be rigorous, we should make a difference. Good. Now, what happens to this energy that is reflected back? What happens? Part of it goes in the space, and part is taken by the atmosphere. And what is the fraction that is taken and the fraction that is instead goes directly into space? It is defined by epsilon. Epsilon is the emissivity or absorbivity. Absorbivity. Okay. And there is an assumption that is always taken, always assumed, which is that the absorbivity is equivalent to the emissivity. What is the difference? The difference is that when you have a flux of power getting into the atmosphere, part is absorbed and part is emitted by the atmosphere. Emitted because the atmosphere also emits part of it. And we indicate it with epsilon because they are equivalent. So let's call it emissivity. Okay, so 1 minus emissivity goes back to the space, and emissivity, the part related to the emissivity, is taken. Okay. So you may think, why you call it emissivity if epsilon indeed is taken, is absorbed? The reason is that we can demonstrate that the two coefficients, emissivity and absorbability, are equivalent. So don't focus too much on the details. Okay, we are relying on a series of assumptions here. Let's just focus on the main concept. There is power that is emitted by the body of the Earth. 1 minus epsilon of this power goes to the space back, and epsilon of this power is taken by the atmosphere. Then the atmosphere basically increases its temperature. But given that the temperature of the atmosphere increases, now we have to consider what is, depending on the temperature, by the atmosphere, emitted into the space and returned back to the Earth. And here we have again epsilon emission by the atmosphere in the space, and it's this far, and back to the Earth. Okay? And then the part that gets trapped here is the part that heats the atmosphere depending on the temperature. And this justifies the model that I have given, that makes a balance between what we get into the Earth and what is trapped in the atmosphere depending on temperature. Okay. And that's it. This is the explanation. And now you know what is the albedo, what is the emissivity. Emissivity by the atmosphere. By the way, also the Earth has an emissivity which is 1. Okay. And because you see that here, basically the Stefan-Boltzmann equation says that depending on the temperature of Earth, get everything into the space, the total amount of this emissivity of the Earth into the space. And then you can understand how the atmosphere can be warmed by the greenhouse effect through emissivity. So the emissivity, which I said of the atmosphere, is about 0.7. With the increase of CO2 concentration, basically increases, and therefore with an increase of emissivity, you get an increase of the part of power that is trapped by the Earth, by the atmosphere. So you have an increase of temperature. Okay. So this sketch is a justification for this model. Now, let me go back to the lecture note. Here it is explained everything, okay, and there are also the numbers. So you understand how a simple conservation model can be applied. Do you have any question? This is an addition to the lecture that I had last time. Okay, good. Now, how to move forward from here? And let me get again the slides. And let me get to this sketch of the model. So there is one thing that I wanted to tell you, a first consideration. Now that we understand how a climate model works, So the first consideration is related to the complexity. Indeed, I talked about millions of equations, and I talked about supercomputers that we need to run the models. Still, we have a problem. It is the computational time. So even if we use a supercomputer, the computational time is very long. It takes a long time, for instance, to say, okay, let's suppose that I reduce the human emissions of 20%. What is the result in terms of temperature? It takes a long time to get the answer. And so this poses a problem because you understand that if you want to test different models, different assumptions, a different scenario of human activity, anthropogenic forcing, then indeed you need to run many computations. You need to run many simulations, and we need a lot of time. We can run these simulations only in few centers around the world. But might be the number of supercomputers is increasing, but actually the number of supercomputers that can run this simulation is not very large. Maybe there are 30, 40 supercomputers available at the global level, and they take a lot of time. So the scientific community realized that this is a huge limitation, because you understand that also if you want to see if a model is reliable, if you want to estimate uncertainty, you need many runs. And these runs have to be also extended into the future for a long time. So it is really a limitation, the fact that we can run only few of these simulations. And therefore, the scientific community wondered how to solve the problem. I already talked about reasonable models, but actually there are some purposes of research questions, and some applications that require a global analysis. So the scientific community was not fully happy with the solution of the regional models. They wanted to find something something quicker. So the idea was, is it possible to describe the same information of a detailed model, the same resolution of the detailed model with a simpler model? Is it possible to simplify the models while keeping the amount of information unchanged? So while keeping the level of detail of the simulation unchanged, is it possible to simplify the model without losing information? You may say that it's not possible because, of course, I already explained that I need to solve the equations at the local level, so I cannot reduce the spatial resolution of these models, because if I want to describe at the local level, I need to keep the same spatial resolution. But the scientific community realized that there could be another possibility, another opportunity, and the opportunity is to simplify the equations. Instead of using like fully theoretically based equations, we use simplified equations, and the simplified equations means a kind of empirical equations. Equations that can reproduce the same results, but with a lower complexity. And so the scientific community devised what are called model emulators, and this is a key word in climate science. Okay. Model emulators. How to describe in simple words what emulators are? Okay. Think of a simulation by a full model that took like 1 month to run. You get a huge amount of data, and a huge amount of data obtained. Why? How? Okay, this is the full model. Let's call it FM. The full model has some input data, input, plus boundary conditions, for instance, plus boundary conditions plus initial conditions. We already learned what boundary conditions and initial conditions are. So I give this input information to the model, and the model produces an output, which is the simulation. Okay, simulation. And this takes like long time. Okay, so the question is, can I take the same input information, give it to a model emulator, and get the same simulation, but with a short time. I'm sorry, I am writing very low in the blackboard, but it is, and maybe that you don't see it. It's short, okay? So I keep same input, I get the same output with a model emulator. And the model emulator is just a relationship, whatever it is, that can satisfy this requirement. Does it exist? So is it possible to find another model, an emulator that gives the same result, but with any kind of relationship between input and output, any kind, not just physical relationship, chemical relationship, any kind of analytical relationship, with the only condition that the computational time is shorter? The answer is yes, it is possible. And it is possible with what is called machine learning. So machine learning is a buzzword today in science. A buzzword means a very popular, very fashionable term, and they are used for everything. Okay, I think they are overly used because machine learning is just looking at what? They look at the input, they look at the output, and they find the simplest way to establish this relationship. They explore a lot of analytical relationship, a lot, until they find a good one, which is very fast and good in reproducing the information. And this process of looking for the best relationship is called training. Machine learning needs training. So I say again, machine learning is a way of modeling that looks at the input, looks at the output, and explores several analytical relationship candidates with the only requirement that they are fast to establish the relationship between input and output. At the end of the story, they find the best one. And this is through training. And once it is trained, the model can be used to generate new simulations. So the idea is, I use the complete model to produce the training data set, and then I use this data set to train machine learning model. Once it is trained, it can be used to generate new simulations. So why did I say that it's overly used, in my opinion? Because, you understand that there is some uncertainty in this process, okay? Because the machine learning model will never be perfect. And there is another reason why I say it is overly used. Because we need to make sure that the model that is trained, the machine learning model, once trained, works also in a simulation. And in technical terms, we say it works in out of training situations. This is not completely true. So, for instance, if you think of a sporting activity like training for a biker over inside a room with these bikes, spinning bike. Okay, train with a spinning bike. You can make a perfect training over a spinning bike, but you have to make sure that once that you go over the road with a real bike, the training that you made on the spinning bike is really effective. So over the spinning bike, you can get a perfect performance, but you are not sure that when you go in a real environment, the training is effective as a very specific training on a real bike. The same here, you get a simpler model, which is training, apparently works perfectly, but when we go in a real situation for which the model has not been trained, there is the risk that the model doesn't work well. Of course, the scientific community elaborated a lot of suggestions for testing the models after training, but still, I mean, we have to be careful still. And so this is the reason why I think they are overly used, because apparently they work really well in training, but when you use them in the real world, I mean, while with the physics, you have a theory supporting you, a machine learning model is supported just by training. There is no theory. Okay. But still, they are very popular because machine learning is very relevant. And by the way, artificial intelligence is a synonym of machine learning. So when I realized that the media gives the feeling that artificial intelligence is a new method. It's not new because machine learning dates back to 50 years ago. After the introduction of the computers, machine learning was also created. What's new in artificial intelligence is the computational capacity. So artificial intelligence can rely on supercomputers and therefore can digest much more information. But actually, it's machine learning is artificial intelligence. And we are told that we have to be careful in artificial intelligence because by using artificial intelligence, because artificial intelligence may be wrong. We know that. Okay. And also we know that artificial intelligence has other limitations, but at least we know that it may be wrong. So also for machine learning, for model emulators, we have to be, in a way, concerned by this potential inconvenience. It may be wrong. But still, model emulators are very interesting, and they allow us to make a lot of applications because really the computational time is limited. So let me give you some examples of what machine learning allowed us to do. And I go here again. For instance, assessing uncertainty. Because if you can run many simulations, you can really test several modeling solutions. And therefore, you can identify the model that works best. This is one possibility. Of course, if you can run only a few simulations, you cannot test many models. But if you can run millions of simulations, then you can really find what is the modeling solution that is best. And this gives a big advantage, allowing us, and I think there is a figure here, just 1 second. I am pretty sure. Just 1 second because I need to find it, but I have a figure here. Okay, this one. What can you see here? You see climate model that is run several climate models actually that is run up to 2100, but it is also run back into the past from 1850. This allows us to test what is the modeling solution that works best in producing the past climate. This was not possible up to a few years ago because, one thing is to run a simulation for 80 years into the future. One thing is to run a simulation for 250 years. So, indeed, model emulators gave us the opportunity to test how climate models work in the reproduction of the past climate. And this allows us to select the models, to make projections by selecting the models. Here you can see in blue the observations of percentage of warming, sorry, not percentage, degrees of warming since 1850. In blue, you see the observations, and we find what we know. So the warming is about 1 degree, 1.3. And you see here several simulation of models, and you see that indeed the climate models, also if you look into the past, there is a lot of scatter. So you see the uncertainty, and then you can find, you can constrain the simulations. What does it mean, constrain? It means that you are rejecting the models that didn't work well for the past, and you keep on the models that worked reasonably well for the past. So you can get a constrained range, and you see the constrained range is in light gray, while the unconstrained range is much larger. You see it's much larger. And you can also see another interesting information from here. The unconstrained range is not only larger, it is overestimating the future temperature. And this is what indeed we realized. So if you make a model selection by using the best models only, then your prediction is a little bit more optimistic for the future temperature. This is very interesting. It means that probably in the model setup, there is something, in the general model setup, something leading to overestimation of the future warming, which is in a way reassuring. So all of these progresses, and also you can see to get the best performing model, and you see that indeed it's quite good. These progresses have been allowed by the use of emulators. Still, be careful. If you look at the best estimate projection, which is the dark, the black thick line, and you compare it with the observations, you can indeed see that still there is a lot of uncertainty. A lot of uncertainty for temperature, not to speak about other variables like rainfall, which are more linear. Okay, this is fine. I mean, this is why we always say that climate models shouldn't be used to reproduce a single point. They are good in reproducing a pattern, but not a single point. So when we look at the past climate, we don't have to compare the average temperature in 1901 with the observed value. This is a meaningless comparison. We should compare statistics over a window of 30 years at least, and we already discussed this. So you should compare the statistics, the pattern, not compare the single points. But once again, we can run many simulations only with, up to now, with model emulators. Another interesting application of model emulators, this is contribution to present day warming. I think this is really something interesting. And it is a contribution to the attribution problem. So what is the reason for the present warming? And here you see that there is a split of the total anthropogenic contribution into several components. What is due to CO2, what is due to methane, what is due to halogenated gases, and I mean, what you can see is indeed the role of the methane is indeed significant. And you see also uncertainty bars, these kind of ranges over each bar of the histogram quantifies the uncertainty. Land use change, etc. And this is something that has been made possible by the use of model emulators. For any figure, you find the sources. And if you want to expand, once again, you have the opportunity of doing that. Questions? Okay. One second, I'm checking if I'm not missing anything. This is another representation of future emissions. It is included here because it's very recent, and it is taken from carbonwaste.org, and it is related to the very recent development of the coupled model intercomparison project 5. What is the coupled model intercomparison project? It is a project that is managed by the IPCC to compare different modeling solutions. And these are the initial scenarios that have been depicted up to 2100, which have been recently updated. And you can find these references also in the IPCC website. Anyway, this is just an information to show you that the science is indeed evolving, also thanks to the model emulators, and it is evolving and therefore needs a really very continuous monitoring. The assessment of climate change, the science of climate change is continuously evolving. And indeed, we can understand the reasons because we are learning, and also the computational resources that we have are steadily increasing. But still, I mean, it is something that requires a lot of updated information. So if I had, for instance, to recommend a book on the science of climate change, I wouldn't be able to suggest a title that includes the very recent developments. This is really a topic that needs continuous updating. And needless to say, in the last couple of months, with the decision of the US administration to divert part of the funding dedicated to research, it is there is a debate that is ongoing, which is probably changing the dynamics and the organization of the research activity around the subject. And for instance, one reason of concern is that monitoring programs may be in a way affected. And you see that we need really a lot of data, a lot of information. And fortunately, today we have a lot of opportunities given by satellites, remote sensing in general. And unfortunately, these monitoring programs need funding. And let's say that if indeed the funding is subjected to cuts, then it may be the progress in science in general and in climate science in particular may a little bit slow down. I mean, above all, it is at any time, it is an interesting question how much funding should be dedicated to research and how they should be managed, because of course there are a lot of priorities which need to be carefully considered. So, I mean, it is a basic question, and how much we should invest in science and how science should be optimally managed. I would say that today, for many reasons, including also the pandemics that we just had, for many reasons, it is a very important question that is on the agenda of several administrations, not just the US one. Okay. Here, there is a long discussion about uncertainty, which I wouldn't really look at it in detail. I just invite you to have a read and to look at the picture, and you can see these figures are quite old. I mean, they are 10 years old, but with the progress of research, the modern progress of research, 10 years are really a lot, really a lot. And these figures really show you, this is a reconstruction from 1900 to 2000 of models, 3 different models, and you see that there are big differences. There is another figure here, and this is, I think it is about 10 years old, maybe 15. And you see that the predictions by different models for the temperature in 2100 are indeed very large. And how is uncertainty estimated? I want to say an interesting consideration. I want to share an interesting consideration with you. So uncertainty is estimated in statistics by comparing simulations with observations, traditionally. Okay. So once again, you get a model simulating what happened yesterday. You compare the reality with the model simulation, and you estimate uncertainty. This is the way statisticians traditionally deal with uncertainty in uncertainty of prediction. Okay. But of course, this is applicable only if you have the opportunity to compare past observations with simulations. In many cases in our everyday life, we don't have this opportunity. So if I want to decide by considering uncertainty what to do tomorrow, based on the prediction of the weather, okay, I can also, okay, this is not a good example. Let's say, if we want to estimate the uncertainty of the outcome of the next presidential election in the US, we don't have historical observations that are representative of the current situation. Not because the current situation is particularly a single one, but simply because in the past we never had the same candidates, never had the same population, never had the same political setting at the global level. So you cannot predict the outcome from the midterm next year election in the US by looking at the past. You have to use a different method. How is uncertainty in climate simulations usually estimated? By running several models and identifying a range. Okay. So let me go back to the figure that I showed you earlier. This one. So they look at the simulation of several models and estimate a range and say, okay, this range here, let's take the full range is uncertainty. Then they have the idea of saying, okay, let's look also at the past simulation, let's constrain it, but still it is a range of model predictions. And they say this is uncertainty. And it is called, in technical terms, the ensemble range. So the range of an ensemble of models. Good. There is one important thing that you have to take into account. When you get an estimate of uncertainty, don't take it for granted. You have to wonder how it was estimated. So in this case, is the range of models representative of the uncertainty that I need? Another way of posing this question, if all the models are wrong, is this a good estimate of uncertainty? Are we sure that the reality will be included in this range, whatever it is, if all models are wrong? Of course not. If all models are wrong, the true value will be outside of the range. So simply taking a range given by models does not suffice to say the future will be inside the range. So there is something more that needs to be added, something that depends on the correctness of the model, on the model reliability. So I have to give at least more weight to the models that are more reliable. This is what I get here with the light gray. I take the models that were more reliable to simulate the past, and then I get the light gray. Still, I am not sure that the future will be inside here. Okay. So how the scientific community is trying to solve this problem? The scientific community is trying to solve the problem by correcting the model simulation. This is called bias correction. Let me write it down because it is another keyword. Bias correction. And let me try to explain again in simple words what it means, bias correction. What does this mean? It means that I select the best models, like those that determine the light gray here, but I make something more than that. For each of these best models, I look at the error that they did in the past, and I correct the prediction based on that. So if I see that these best models, something of them overestimated the past temperature, then I correct the prediction based on the overestimation, the same for underestimation. So besides selecting the best models, I try to correct them by looking at their reliability in the past. This is called bias correction. Or there are many synonyms, similar terms. For instance, quantile delta mapping, let's forget about the details, or correction of statistics, which is a synonym of bias correction. And there is a huge literature. There are several questions, of course, how to compute this bias, how to compute this mistake. Should I look at the average mistake in reproducing what? Local data, global average, local average. So there are several contributions in the literature. Personal opinion, I am very skeptical about bias correction because if a model is wrong, it's wrong. So I don't really like bias correction because it looks like I make a model, the model is wrong, I make another model to correct the mistake of the wrong model, which is, you understand, it is something that looks like eternity, you know. And I think we should make an effort to improve the models rather than concentrating on models for correcting the models. It is circular. It doesn't help very much science, and I'm not very confident, and I said it's my opinion. Actually, I have to admit, it's a basic question in climate science. Should we use bias correction or not? It's not only my opinion, I mean. And also, it is not something that I elaborated myself. I have to admit, it is, studying the literature, I recognize myself in those that are criticizing the literature on bias correction. Okay, now I would like, let me get the slides. Okay. I have to refer to the web page because the slide is not really, but actually, 1 second. Okay, actually, it's it is a narrative. It is very narrative what I'm going to say. I would like to talk about, to start talking about actions. So today I start talking about science. We talked about a global radiative model of equilibrium. Now let's start talking about actions, solutions, okay? Because the purpose of this course, of this educational program is not just to talk about the science, but also to discuss the solutions. And we already mentioned the difference, we already discussed the difference between climate change mitigation and adaptation. Mitigation means that, basically means decarbonization. So it means that we try to avoid climate change, to go back to a previous state of the Earth's climate, previous with respect to climate change. And adaptation means that we accept climate change and try to adapt to it. And we already discussed, mentioned that the time and spatial scale of mitigation and adaptation are much different. Adaptation has to be performed at the local level, mitigation at the global level. And the time scale of adaptation has an immediate effect. Mitigation is means decarbonization, and therefore we have to wait, provided that we can indeed reduce human emissions, so we have to wait for this reduction, implying a decrease of temperature, which is a long time scale. Okay? Adaptation, let me give an example. The very significant example of adaptation is an insurance. So I realize that my house is exposed to flooding. I activate an insurance, I make an insurance to protect myself from the damage. This is not solving the problem in physical terms. It is solving the problem in economic terms, which may be fine. I mean, if my main concern is the economic damage, an insurance is perfect. It may, to some extent, give the opportunity to, in a way, to after a flood, to get more protected in a more effective term. Another example of adaptation is waterproof buildings. This is a possibility. We need money, but we can waterproof a building. And actually, this is a solution that is quite often used. Another example of adaptation, again with respect to, not again, with respect to heat waves, is air conditioning. Air conditioning is an adaptation. In the hospitals, of course, we give priority to air conditioning in the hospitals because, especially if the earth is under threat, then with air conditioning, course, we can solve we can mitigate the hazard given by heat waves. So, what are the solutions that can be applied? So let's focus first of all on mitigation. Mitigation, we associate mitigation basically to the reduction of human emissions of CO2. And what solutions can we mention? First of all, international agreements, like the Kyoto Protocol, it was the first one, and then the Paris Agreement, and all the agreements that we try to stipulate during the COP conferences, the climate change conferences. The last one has taken place, I think, in India, it was end of 2024. And in these conferences, international agreements we try to set up international agreements to promote organized decarbonization. Organized, we need to organize it because, of course, it cannot work at the local if only action at the local level are taken. We need a consultation, we need an agreement in international agreements. You know that today it is these international agreements with the recent decisions in the United States are a little bit under threat because once again, we need a global effort. So this is a possibility for mitigation. And of course, keep in mind that decarbonization has a very relevant social cost. We already discussed it. This means that at the end of the story, it is people that have to take the cost because relevant cost, it means in terms of public money. So it is not just enough to get an agreement with the head of states. We need to get also the agreement of people. And the cost for people is really a monetary cost. It's not only a cost in terms of changing our habits. It's not only not using the car, but using the bus or using the train. It's not only that, or not using the plane. It is really, we need money for promoting decarbonization because we need to change also the production chain. We need to change our industrial organization. And these efforts require really money and require taxation, for instance, a carbon tax, and at the end of the story, it's a cost that is sustained by people, and in particular, this may be a problem, particularly in emerging countries, in low GDP countries, where GDP stands for gross domestic product. And so there are other solutions not mentioned here to reach the target of mitigation. And the solution is still costly, but relies on what we call geoengineering. So solutions for carbon sequestration or for reducing the incoming solar power. Or, for instance, solutions for damming parts of the sea in order to avoid a global sea level rise. And for instance, in Venice, the MOSE, which is the system for protecting Venice from the high tide, is a solution that is based on damming the Venice Lagoon. And another solution of geoengineering which is used is to put coverage over the glaciers in order to preserve the glaciers from melting. Or you may have heard that there is a discussion, a scientific discussion on the opportunity of realizing kinds of screens for reducing the solar power, screens in the atmosphere with several different methods, ranging from artificial emissions of particles that create a kind of umbrella, and other methods relying on the realization of a real screen, which would put into the orbit or something like that. And, you know, these solutions, or you may put a dam on the Gibraltar Channel in order to keep the sea level of the Mediterranean, separate the sea level of the Mediterranean from the sea level in the ocean. These are experiments that are mentioned. It is a very controversial topic because even climate scientists are a bit skeptical about the side effects. But there is a lot of literature on these geoengineering programs. If you're interested, you can just Google and see that indeed Bill Gates, for instance, was proposed a solar screen and was willing to put money in it. So, but there is, as I said, it is very controversial because you understand that you could trigger some tipping points, it may reach some side effects that may generate tipping points, changes of equilibrium states, and so it is very controversial. But in the literature, there is really a lot of discussion on that. And given that it's controversial, there is also some arguing, you know, some arguing because some people say that the funding for research shouldn't go in this direction because it is too fantascientific, I would say. Okay, but it is still interesting. I read something because I was interested in trying to understand what are the solutions that are more popular, more considered. Okay, and for sure, the coverage of the glaciers is already done. And also in the Alps, they put a cover during the summer over some glaciers to protect them. They do that because they want to save the room for the skiing industry. So there is a very specific reason for doing that, but it is already a usual practice. It is probably more interesting to discuss about adaptation because adaptation, it is something that it's frequently overlooked, not considered, because it is considered like a medicine, not a real remedy. Okay, it's like a therapy, not a real solution. But actually, I mean, I think it should be more considered because if you have a real problem, and today, for instance, in Bologna, we have the problem of flooding, it's clear that, I mean, recently, it's clear that there are more frequent intensive rainfall events. So on Friday, we got a red alert, and I think it was like the fourth this year, maybe, or the third. And in the past, it was not like that. It is clear that, I mean, Bologna is, from an hydraulic point of view, the drainage system of Bologna is there from, I would say, from 1960. So it's already kind of 70 years old, and the frequency of flooding, I mean, we had flooding also in the past, but the frequency is clearly increasing. So we have a real problem. It is also the numbers speak for it. So it is not under question the fact that in terms of flooding, urban flooding and flooding in small areas, small rivers, there has been an increase. So I think the problem should be solved. I mean, whatever is the opinion of people, of scientists about climate change, what is the contribution of CO2, what is the contribution of methane, what is the contribution of natural variability, whatever it is, I mean, we have a problem. So the problem has to be solved. Like in the past, when they had flooding problems, they created levees. When they wanted to recover the land from marshes, they built drainage systems. through canals in order to reclaim the land that was previously invaded by water. So, I mean, this problem has to be solved, and we cannot overlook it. So, what are examples of these adaptation policies? And first of all, you can see here a list of behavior of the considerate system, like the city of Bologna is a system. We can call it a system. And behavior of the considerate system, behavior of climate change that should be taken into account when designing an adaptation policy. And the list is, of course, not exhaustive, but it is an attempt to emphasize what are the most important things to consider. The variability of climate change and the way in which climate change is taking place in the considerate situation. Like in Bologna, it's not a problem of the long duration rainfalls. I already mentioned this. It's a problem of the summer storm, of the very short rainstorms, the rainstorms that last for a couple of days. It means that climate change has been effective on the short term, on the short duration rainfall, not on the rainfall that lasts for a couple of weeks. And this means that the problem is particularly relevant for small urban catchments, for small catchments like those that run down from the hills over Bologna. Okay, so we have to really try to understand it and to quantify climate change. And then the effect of climate change may vary across demographic groups or across portions of the city. It's not the same in the upper city of Bologna and the lower part of Bologna. We have to consider it. Climate change okay, poses both risks and opportunities. Yeah, that's true. First opportunity in Bologna is that we may indeed reconsider reorganizing a little bit the drainage system in the city. And you get these incentives to think about how to improve when you get in a situation that is risky, a post-serving situation. And okay, these are. But what I really would like to do is to try to provide a list of these possible solutions. But let's make a break first. Questions? Okay, give me 15 minutes and then we move forward. Let me close the micro and the webcam.
But that was like people just you get the same piece. The first is yeah.
Okay, so one second. I want to get to. Okay, good. So, everything is, yes, working. Some examples, these examples of climate change adaptation actions have been taken by a lecture that is linked here. We are now discussing the lecture on climate models, and here there is a link to another lecture, which is, the link is here. More details can be found in my lecture, Climate Change and Water Cycle. This lecture is not part of this course, but I take it just 1 second now for giving you some examples of actions that can be taken to reach the target of climate change adaptation. 1 second. Okay, these are here. So these examples are, I read just some of them. Installing protective or resilience technologies and materials in properties that are prone to flooding, changing to heat tolerant tree varieties, or installing better flood defenses such as seawalls and increase the pumping capacity when there is the risk of flood. Of course, increasing the pumping capacity. Pumping is a solution to mitigate the damage after flooding, raising street level to prevent flooding. These are actions, examples of actions that can be taken. And the list is not exhaustive. There are several, depending, of course, on the kind of hazard the community is exposed to, which can be flooding, water scarcity, can be heat wave, can be storms, wind storms, rainstorms. Depending on the hazard, we can find a variety of solutions, a diversity of solutions. The question is how to design them. Okay, so how can we, if we want to raise the street level to prevent flooding, how much should I raise the street level? And for any of these actions, you see that there must be a design behind. Or, for instance, if I activate an insurance, what should be the max damage? Because of course, the price of the insurance is larger if I increase the max level that can be reimbursed, the max amount that can be reimbursed. So what is the max amount? How can I evaluate these design variables, these project variables? And it is important to evaluate them because, of course, the risk of flooding depends on climate change, on the expected future weather, depends on other evaluations that I should do. So how can I design these actions? First, of course, we need predictions of future weather, and we already know that climate models can give these predictions with uncertainty. Usually when you make a design project, you need also to estimate uncertainty, because without estimating uncertainty, of course, you cannot evaluate the future risk in probabilistic terms. But there is also another, and therefore, how to get these future climate scenarios with uncertainty estimate, and how to identify priorities. Because let's suppose that even if, let's suppose that we had a perfect prediction of future climate, then we get an increase, probably, an increase of the hazard associated to multiple perils. So we may have an increase of the hazard associated to flooding, an increase of the hazard associated to heat waves. And of course, our resources are not unlimited, especially in countries with a large public debt, in countries with less resources. So how can we find priorities? And it is a very interesting question. It is an interesting question because it's a question that is not only related to engineering, it's related to social sciences at large. So to find an answer to this question, how to identify priorities, how to get a good estimate of future climate is really a multidisciplinary problem, an interdisciplinary problem. And it is setting priorities needs a perfect knowledge of each peril, of each damage associated to an individual peril. So how to decide, and how to decide also in a democratic system. In the past, it was relatively easy. Priorities, or let's say, not only in the past, in a governance which is top-down dominated, like, for instance, in a governance where decisions are taken from the top. And it is relatively easy because there is a government or a person that is in charge of taking the decision from the top-down decision, which decides, who decides. And then typically this happens when there is a top-down system which is not subjected to elections, because when the governing system is subjected to elections, then there are more constraints in the decision process. A person that is not subjected to elections takes the responsibility and decides, and then the outcome, I mean, may be negative or positive, but in any case, the person is not concerned by the impact, the personal impact of the decision in terms of visibility, in terms of popularity. In a democratic system, there is the government that is periodically rotating and subjected to elections. And therefore, the decision-making process is more complicated because in a democratic system also we have to seek approval from the parliament and then from the citizens. So how to take urgent decision, how to decide in terms of climate change mitigation, adaptation in the contemporary society. This has promoted the development of a particular branch of science, which is decision theory, how to take decisions. And I want to mention, just to give a very basic information on what are the modern visions in decision theory. So how can we decide priorities and how should we also consider decision-making in the presence of uncertainty, like in climate science. And I want to refer to a figure that you can find, not in the slides, but you can find it here. 1 second. And the figure is this, sorry. Because this is the other lecture, let me go here, okay. The figure is in the lecture that you find in our website, in our webpage. Okay, this is the figure. Let me just open it in a new window because, okay, so we can resize it. Okay, so let's focus on the so-called traditional approach, top-down. And this is, you can interpret top-down both in a political, with a political meaning. Top-down means there is a person or a body that takes a decision and imposes it. But we can get an interpretation of top-down also in the scientific context. In the top-down approach, in science, what we usually do to design climate change adaptation is to start from climate models, future scenarios, and then climate models give us the design variable. With design variables, I mean project variables. So, for instance, extreme rainfall, extreme temperature. So a variable that defines in a way the hazard I am subjected to, okay? A project variable if we have to carry out a design project. And then from the design variable, we set the strategies and we design our projects, okay? And therefore here you can read vulnerability of system and strategies. Strategies means also include also our possible project. This is the top-down, and usually here, to get the future scenarios, you have a modeling chain, a chain of models, like a climate models first, and then maybe subsequent models to estimate these project variables. Like, for instance, if your peril is flooding, you need a climate model that gives precipitation. Usually the climate model doesn't give river flow. And then you need a subsequent model, a next step model, which translates rainfall into river flow. So you have a cascade of models. What is the limitation of this approach? The limitation is that a cascade of models means also a cascade of uncertainties. And the limitation is that if your future scenario, in a way, is not reliable, here you are missing a kind of verification. And you are missing also consultation with people. And here we find a kind of connection with the political system. So this top-down approach is really missing a connection with people here. And therefore, modern decision theory proposed to revert this workflow from top-down to bottom-up. And here you see two examples of decision support systems with a bottom-up approach. Let's try to focus on on the second one, okay? What is RDM? What is RDM? It's called robust decision making. In this workflow, we start from possible solutions. So we don't start from a climate scenario. We start from what can I do? And what I can do is, for instance, getting protected against floods with flood-proof buildings, or getting insurance. So we have a sort of strategies, and then we then get the scenarios, the climate scenarios, in a second step to check if the strategies are successful. Okay? And then if we see that according to the scenarios, the strategy seems to be successful, so like flood-proof buildings, according to the climate scenarios, are resisting to the future flood? Yes, they are. Okay. And then basically I see if this strategy solves the problem. Solves the problem. So the vulnerability is resolved, is improved, is mitigated. Vulnerability is mitigated. The hazard is mitigated. Okay. And then I can, if yes, I can elaborate and test new strategies, and then I get back to the scenario. What is the difference here? The difference is that I start from the strategies, I start from the solutions, I start away from the people. Because, I mean, when I start by considering possible solutions to the problem, I start from the people. And also when you present to your audience, one thing is to say, look, this is a model that gives me the future climate. Another thing is, look, we have these possible solutions to your problem. And when you evaluate the strategies against scenarios, you discuss with people. This is what also the laws and the guidelines in Italy suggest. We have to open a consultation with people. Another possibility, instead of starting from the strategies, I start from the problem. Like I got flooded. Okay, this is a problem. I got an heat wave. This is a problem. So assessing vulnerabilities means let's start from the problem. And then basically I look at the future scenarios in order to see if the problem in the future will be larger, will be increased or mitigated. So I start from a problem that I have now. In Bologna, we have frequent flooding. Okay, let's look at the future scenario. What is going to happen? Okay, but the future scenario is used as a verification, not as a starting point. Okay, and then I can get further information. This method suggests that I get also other information besides future scenarios, like, for instance, a prediction of future climate obtained with a statistical model. Okay, and then I elaborate a strategy. I make a design, a project to resolve these risks. So what is the advantage here? The advantage is that I start from a problem that is already here. So at least I find a solution to a problem that today is a problem. So I'm not relying on a model, I rely on facts. Like, let me start a solution to avoid flooding in Bologna. And then I check with the future climate scenario if the solution is going to last for just 10 years, 50 years, or 100 years. But still, I start from a solution to a current problem. And what happens if I see with the scenarios that the solution is going to last only for 10 years? Then I try to make the solution flexible. So I solve the problem with a method that if in 10 years I have a repetition of the problem, I have the problem again, then I can correct. I can update the solution. And this allows us in a way, also to try to be efficient in terms of use of resources, in terms of our commitment to try to solve as many as problem as possible, because they can make a rational use, an efficient use of the resources. So I hope I clarified what is the modern vision. Start from current problem to deal with uncertainty by trying to find a solution that, no matter the uncertainty, is still useful. Okay, and this is what is called also a resilient approach, a no-regret approach. Okay? Resilient means that in a way we improve our capability to react to shocks. No regret means that whatever the future is, the money that I spent today is no regret. What I'm doing today is no regret. This is the modern vision. What is the problem? Because you may say, okay, but this is quite naive. Why did we invent this workflow before? The problem is actually the consultation with people, because this consultation with people, whenever you propose to use resources, public resources for reaching a target, your consultation with people will always lead to some confrontation, really. So to some diversity of opinions. And this diversity of opinions in a democratic system where the governance is going to be re-elected may generate concerns and may end up with doing nothing. This is why very often today we don't do anything. I mean, the governance is not able to be effective, to reach effective solutions. And the reason sometimes is that, the confrontation with the public is part of the politics, but it is not easy. And sometimes the governance is concerned by the consequences, the implications for visibility, for their not only personal interests, it's also public interest. I mean, a good governance is committed to reach the target, to get the target. And therefore, of course, the loss of credibility, the loss of popularity is undermining the opportunities to get the target in the public interest. So it's not only a problem of governance that has vested interests. It's not only that. Of course, it can be a problem of vested interest, but it's also a problem that in a democratic system, indeed, in a democratic system, a necessary condition for success is to get the approval, at least of the majority of the population. If you don't get the approval of the majority, you don't get the target. And therefore, in a democratic system, we need a kind of support to decision making. And this is why in the past we used the top down. Top down, I mean, if the persons taking the decision are well informed, are wise, and motivated to pursue the public interest, it's fine, because they are not concerned by losing the popularity. They are just committed to, if they are good. I mean, if they have good motivation, they are committed to reach the good for people, and then they have the opportunity of really deciding, of really do things. In a democratic system, this opportunity sometimes is undermined by this confrontation, this discussion with people. It is indeed a complicated problem, but I am optimistic because I think that these processes are an evolution. If we thought of showing a slide like this 40 years ago to students, I mean, it would be like something like fantascienza, something like fiction. Today is a real opportunity, and we already have some cases of applications of these bottom-up approaches that were very successful. Okay, so 1 second, because, okay. Okay, here we are. I would say that with this lecture, we are okay, and we are done. Do you have any question, by the way, while I check if I didn't forget anything? When you read these notes, you will find things that I didn't explicitly discuss. Because, as I already explained to you, I tend to give more information with respect to what you need for taking the exam. And if you are concerned, and at a certain point you will be, by preparing your exam, just refer to what I discussed, and the questions in your quiz will be very specific, and be sure that I will not put any question there that I didn't discuss explicitly in the room. Okay. Okay. So I think we can move forward to the next one. I wanted to show you this figure, sorry. So I found something that I forgot. This is an example of carbon sequestration with geoengineering methods. So basically, this is, just 1 second. Okay, here it is. This is, in this sketch, you can see that there are geological formation where CO2 is stored. And in particular, you see the mention to depleted oil gas reservoirs. One solution that we are trying to apply, and in the United States, there are already some plants that are doing that, is to sequestrate CO2 from the atmosphere. So to through filtration by membranes, we capture CO2 from the atmosphere and we inject the CO2 into the depleted oil gas reservoirs. This is a typical geoengineering solution. And it is, there are some doubts on the effectiveness of this because, you know, these reservoirs may be subjected to leaking depending on the pressure with which we inject the CO2, there might be some leakage from the reservoirs to the atmosphere. So it is something that it is not necessarily effective, but still it is something that we try today to do. Okay. Okay, so let me just go back to our previous. Okay. Okay, fine. I found the visualization that I wanted to reach. Okay, decision made. Okay, perfect. Next one. Okay, the next one is a link on my lecture on climate change and water cycle. we are not lecturing this. I think there are many interesting information. It is very narrative, the discussion here. And you see that there are some graphs, many figures, some graphs that give in more detail a quantification of climate change, greenhouse effect, etc. And there are interesting also graphs related to the variability of some time series which we observed close to here. This is a 3D representation of the Po River flow, and it is daily flow of the Po River along the years and along the days of the year. So you get a 3D representation because on the vertical axis you have the river flow, and on the two horizontal axes you have the years and the day of the year. And it is interesting to see that there is a great natural variability. Just 1 second, a quick reply. Francesco, lezione fino alle 4, ti richiamo. Perfetto, ti richiamo che ho lezione fino alle 4, va bene? Non mi senti? Ah, un attimo. Adesso mi senti? No. Sì, sì, dopo le 4, ok? Figurati, ciao, ciao, ciao. So I apologize, but I have a urgent question to deal with and I had to reply. And then there are other time series here of daily rainfall in Bologna. Let me just check. There are some interesting figures on sea level rise observations. And just let me scroll down. Okay, here there is, okay, rainfall series in Bologna, this one, from 1813. So, moral of the story. This is for you, for your personal information. There are no questions on the exam on this lecture, okay? And my suggestion is, I think it is not a difficult reading. So if you feel passionate about the topic, I think the connection between climate change and the water cycle is really an interesting reading. And but just for your personal education and no exam on this, okay? Now, let me introduce now the next topic. It's history of Earth's climate. Why I am, and here the slide is not available in the public domain. So you have to log in into Virtuale and with your credential. Of course, now I'm logging in with my credential, but you, of course, you don't use my credential, but yours, okay? And here you get the page of the course on Virtuale. We already discussed it. And here there is the lecture notes and the lecture notes on history of the Earth's climate. Let me see if I can succeed in getting it full screen. 1 second. Yeah, here it is. Okay, this is not publicly available because the slides are sorry, see if you can avoid to speak because it looks like I cannot listen while I listen everything, and unfortunately I get distracted. And this is courtesy of my colleague Veronica Rossi. And the slides, unfortunately, cannot be shared in the public domain because there are some figures that are protected by copyright. So let me just introduce why this lecture. This lecture means to give you some information for understanding what we call natural variability of climate. We use the term natural variability to identify the changes in climate that we don't attribute to human influence, not attribute to anthropogenic impact. how do we define the anthropogenic impact? We define the anthropogenic impact as the increase in CO2 emissions due to human activities. This increase, we assume that it started after the Industrial Revolution. The Industrial Revolution is located between 1850 and 1900, depending on the country. We also know that in these years, the Industrial Revolution caused a lot of air quality problems, like increase of dust concentration, several health problems, because of course it was the Industrial Revolution was based on the production of energy through vapor generation, and therefore water vapor generation, which was obtained by burning very crude fuels like wood, like they were fuels producing a lot of emissions without the use of filters because people didn't realize that the massive production of steam energy would cause an increase of the air pollution. It is the same thing with the river pollution. People didn't realize that using the sewer system, the discharge from the sewer system into the rivers would generate a drastic reduction of the river water quality. So we locate the beginning of the anthropogenic impact on climate in the years between 1850 and 1900. So anything that happened before, we assume is due to something different, not related to humans. It is, it is an assumption that may be questionable, but we take it as an assumption. And therefore, all the climate changes that occurred before 1850, we assume it's given by natural variability. It is extremely important to study these changes, this fluctuation. You understand why? Because we cannot really understand human-induced climate change if we cannot correspondingly understand natural variability. So the study of the past climate is a very topical issue in climate science. This is why I think it is important that we try to get an understanding of how these past changes are studied, because we don't have measurements, or we have only very sporadic measurements like flood marks. Flood marks are an important piece of information. Usually in cities, when they get flooded, people used to mark the flood level, the water level during the flood. These flood marks are, of course, a useful information to understand past changes in flood frequency. So we don't have, in general, direct information, direct data. We don't have temperature observations prior to 1850. We have few observations of rainfall prior to 1850. And therefore, we need to find other ways like ice cores, tree rings, which I already mentioned, to study the past climate. And actually, the information that we get is very relevant, very important. So what kind of, and here you see a statement that the past is the savior for the future, which in a way influences the motivation for this lecture, okay? So what kind of records we study? Okay, here you see a quote from the geologist Charles Lyell already, 200 years ago, which stated that the present is the key to the past. And what he meant to say is that the present situation is a consequence, a direct implication from the past situation. And but still, you see, our knowledge of the past can strongly improve our understanding of the present world, especially in environmental sciences. If you are interested in the movement that was called uniformitarianism, it was a scientific vision, a scientific concept that indeed stated that understanding the present is the key to understanding the past. And but however, the opposite is also true. This is why we look at the past. So what kind of data do we use? We are going a close for today, but I just want to give you a first example, the geological record. The geological record is what we use also to define the eras, the periods, the epochs. The geological record is an indicator of past climate, is a natural laboratory, as you can read here. And so it is the key to our understanding. And with the geological record, you can see here the Scala di Chimica e Agrigento is an exemplary example of stratification after several cycles of sedimentation, which gives a unique opportunity to look at the past climate. But with the geological records, the geological records are much more extended and include also the analysis of the sea bottom, the analysis of lake sediments, limnology, the analysis also of ice cores. Ice cores are actually, you cannot define them as geological records because geology refers to the genesis of the soil and the rocks. But still, it's an example that by studying the underground in general, we can get an information of what was the climate of the past. And it is an interesting exercise to compare the result from this understanding with the climate models and projections. But I would say that for today we can close here. Questions? Okay, thank you very much.